All right, let's get started. Well, good morning. We're going to talk about traits, mixins, and monads in this presentation. My name is Venkat Subramaniam, and we'll look at quite a few examples along the way and understand what these concepts are. Best time to ask questions or make comments is when you have it, so please don't wait till the end. Anytime is a great time for questions, comments, anything you want to ask. I'm blinded by these lights, so if you raise your hands, I won't be able to see you, unfortunately. But do draw my attention, start asking questions or say a few things. Then as soon as I draw your attention, I'll walk around, I'll try to see where you are and definitely listen to you. So don't hesitate at all. So we're going to talk about actually two independent or separate topics over here. One is related to traits and mixins, the other related to monads. And what I'll do is I'll roughly divide this into two parts. We'll do about 75 minutes of traits and mixins, talk about various different details. Most likely get started into monads if we make good progress. And then the rest of the half of the presentation, I'll talk about monads themselves and what those are. So let's get started with traits, and then we'll come back to monads after that. Now, one of the things that quite fascinates me is learning about certain concepts, and sometimes it's fascinating to see that we would read about a concept or be intrigued by it, but sometimes you have to wait for decades before you actually get to use it. I remember spending the summer days about 20 years ago reading about mixins and only wondering how cool it would be to use them, and didn't really have options to use it at the time with the languages I was programming in. And I'm sure there were a few languages that supported it, but definitely not mainstream languages. And even today, mainstream languages don't support mixins, but we have had languages that are available on the JVM that has brought these kinds of concepts much more affordable. So it's really fun to see certain concepts that we have been reading about and learning about can be applied. A lot of things have happened recently in that regard, where we are able to apply certain things that we may have only read about. For example, functional programming style is a reality in Java, for example. So that again is very exciting and things like that. But let's talk about modeling for a second. Well, in object-oriented programming, we often use inheritance, and we know inheritance is one of the most abused concepts in OO programming. But nevertheless, inheritance is very useful to create an option for us to extend from a class, in other words, to be able to reuse that abstraction. In terms of reusing an abstraction, the idea really is we want to not only be able to use that class, but also be used as that class wherever it makes sense. So substitutability is very important. But having said that, when we use inheritance, we got a class that provides a certain set of functions and we want to inherit from it. Well, then comes the question, what if we want to inherit from multiple classes? Now, let's think about multiple inheritance for a minute. Anybody with the C++ experience here? If you, a few hands reluctantly. Okay, more people. It's funny how people slowly raise their hands because they're not sure if they want to admit in public. That's okay. That's perfectly fine. I did about 20 years of C++ myself, and I still consider C++ to be one of my most favorite languages for what it was worth when I did it. And it's a lot of fun, but unfortunately, though, there are enormous amount of semantic complexity in the language. But when it comes to inheritance in C++, we could inherit from a class, but you could also inherit from multiple classes. But quickly, when we start programming in C++, when we use multiple inheritance, we quickly realize that multiple inheritance is like a gorilla. It is really cute when you see it in the zoo, but you don't bring it home, right? It causes havoc. Well, with multiple inheritance, what really happens is when you inherit from two classes, you are beginning to make use of the implementation from two classes. That in itself is not really bad until very quickly you realize that two of your base classes end up having a common base class. This often is referred to as the diamond problem. Well, the problem with the diamond issue is that when you have two base classes and the two base classes share the common base class, well, you end up having a duplicate copy of the common base class in your object instance. So if you have a base and you have derive 1, derive 2, and a child, now when you create an object of child, because child derives from base, derive 1 and derive 2, and both derive 1 and derive 2 have a common base class base, now you end up having one object of child within that little instance of derived 1 and derived 2, and two instances of base, and that becomes a mess. Well, to deal with that in C++, you have to mark it as virtual base class, and then once you mark it as virtual base class, the compiler is smart enough to optimize this and say, well, you need to have only one instance of derived of base. Well, that only begins, ends that problem and begins another problem. Methods end up colliding as well, and it becomes absolutely a mess. Well, Java fixed this problem really well. It said no multiple inheritance for you. That is called run away from real problem pattern, right? So that didn't solve multiple inheritance. It just didn't give it to us. But the problem didn't go away. We just avoided the problem. And of course, in Java, we use multiple interface inheritance, and we don't use multiple implementation inheritance. But even Java doesn't address this problem thoroughly, because what happens if two interfaces end up having exactly the same methods? Well, their signature is going to be the same because interfaces don't have an implementation. We can provide the implementation of derived classes, but if you look at languages like C#, they provide a little bit different. They call it as, you are actually able to provide specialized implementation of interfaces in C#, a concept that quite doesn't exist in Java. So when you look at different languages and how languages work together, it's pretty interesting to see some of the features in one language not being available in another, but provides us a certain set of functionalities and features. But the problem of multiple inheritance simply doesn't go away. It still is kind of lurking in the background. So let's think about what we can do about a problem, and then we'll come back and solve this using Java, and then realize that this really is not a solution at all, and then we'll go back and try to see if we can solve it in a better way. And the solution I'm going to provide is not available in Java entirely, at least. With Java 8 default methods, we have a little bit of the capability, but not quite. So I won't go into Java at all after our initial discussion, but I'll be focusing more on Scala and Groovy to show some of the ways that we can do this, and we'll talk about what that is. But the first step in solving a problem is to understand what the problem is. So let's start with that first. So what I want to start out here with is a little example. As you can see, this is a Java code, but I'm going to create a class called human. And my class human is going to have a method over here. We'll call it as a listen method. And within the listen method, I'm going to simply output, let's go ahead and say string over here dot format, and let's say I am, and I'm going to provide a string, and then let's say listening. So in this case, I'm going to simply print the name over here. Now, what in the world is name? So we could define a public final string name, which we can initialize definitely when we create the human constructor. So we'll say the name over here, and then we will simply set the name to be the given name itself. So now that we created a human class, I want to be able to go ahead and use this particular class in whatever we are doing in this particular example. So what am I going to do with the human class? Let's fix the error that I had a second ago. So let's see what anybody sees the error so far. So in this case, that I'm in the sample class, that's perfectly fine. So let's come back to that and see what the error could be. I need to lower the font here so I can see the line number where the error is, so bear with me for a second. So it's complaining no suitable method, of course. So it's complaining over here in the print line method. So that's because I moved this outside my, there we go. So this comes outside, there we go. So given this, let's talk about what we're going to do with this human class. So I could create, for example, human equals, let's say, new human. We'll create an object of this human class. And I'm going to provide another method. Let's say, in this case, the method I want to provide is called seek help from. And this is going to take a human object. We'll call it as a friend for a minute. And then I'm going to say friend.listen, and I'm going to call that particular method. Let's go ahead and call this method and pass Sam over to that particular method. So very simple implementation. We have a human class, and then what we have after that is really a instance we created, and we passed it to this particular object. Well, as you can see here, I don't use any slides. I type code and play with examples. If you're interested, you can download the code examples from this URL, and I will make sure this is available in the bottom as well, so there's no rush for you to note it down right now. So given this, we have the object that we created. But if you look at this particular example, we have a method called listen. Well, the listen ends up being in this class called human, but what does listen has to do anything with human? So let's think about this for a minute. Who listens? Yeah, that seems to be the problem. Nobody anymore, right? But if you really think about it, who listens in reality? Well, I was teaching this session once, and there was one person in the front row. He was very eager and really charming. Immediately he raised the hand. I said, so you know somebody who listens? I said, yes. I said, who? He said, the wife. And we all kind of laughed, and I said, how long have you been married? He said, 2 weeks. I said, I'm really sorry, but that's going to change very quickly, right? So we have this thing called selective hearing with spouse. I travel a lot, so I'm very rarely at home. But whenever I'm home, I want to be really home. But I also like to work, so I often sit down in the kitchen, and I work in the kitchen. So everything seems to go really well, because my wife says, this is great, you travel a lot, but when you're home, you are here in the kitchen, so I could talk to you. Well, everything went fine until one morning. She was talking to me and I was working away, and suddenly there was absolute silence in the house. And then a few minutes later, I realized there's no noise at all. I quietly lift my head, and she's standing there staring at me and says, I asked you a question 5 minutes ago. I will not repeat it. I want an answer. I was really busted right there, right? So this is called selective hearing. We don't hear often. So, well, we could say a friend listens. Well, a friend, that's what a friend is for, right? You go after a very tiring day and you say, you know what, this job really sucks. And what does your good friend say? Your good friend says, talk to me about it, let me listen. A bad friend says, maybe you suck, not the job, right? That's how you know who your good friends are. So a good friend listens to you. Well, there is one good friend who always listens to us and never speaks back. What am I talking about? The dog, absolutely. Well, I want to implement the dog right now. Well, how do I implement a dog? Well, my initial thought was, well, dog, but I know that human has listen, so we could say dog extends human. No, dogs don't like that. So this is a very poor inheritance model for the sake of reusing the listen method. So what am I going to do? Well, we got to figure out a way to be able to send a dog as much as a human to the seek friend method. In other words, I should be able to do something like this, right? I want to say dog buddy equals new dog, and I'm going to say this is buddy, and then I want to say seek help from, and I want to say buddy over here. So let's think about this for a second. If we want to do this, what would be the solution in Java to be able to pass both the dog and the human to the seek help method? What suggestions do you have to fix this? An interface, ta-da, that's correct. So what do? We would first create an interface called the friendable interface. Doesn't that sound so nice, right? So friendable, that just sucks the life out of you, right? But that's a friendable interface. And what am I going to provide here? A listen method. That's great. Now I come down and I say human implements friendable. And so we'll say implements friendable. And then dog also implements friendable. That's great so far. But I need these methods in the dog. Maybe the implementation is fairly similar. So that's going to be in the dog class. So we'll make this a dog. And then what am I going to do? I'm going to come to this guy and say, this is going to be a friendable friend, and I'm going to make that work. Yay, that worked so far. But that pushed us from one problem to another. Now we are able to receive human and dog in the seek friend method, but notice what we just did here. We duplicated the implementation of the listen method in both classes. Anybody who really enjoys duplicating code? No, not really, right? That's the easiest way to lose friends in life, right? Nobody would hang out with us if we just keep duplicating code. So we want to reuse that code. This method could be complicated. Here is a trivial example, one line of print, but imagine there is quite a bit of work you have to do to listen. Well, you want to reuse that code. So how can we possibly reuse that code? Any suggestions? Abstract method. So notice where we're going with this. Let's go ahead and create a class over here. We'll call it friendable. We'll call it as, friendable IMPL. Don't you all love that IMPLs, right? Friendable impl, and that implements the friendable interface. Well, maybe not. It's got the friendable. And then what am I going to do with this friendable now? Well, in this case, I'm going to write a method public, let's say, void listen. Well, I'm going to pass a name over here, and I'm going to move this common implementation up to here for a minute. So I moved that method up to here, and now you can see the listen method is here with that particular name that it can implement. And what we could do in this case is we could even make it as an abstract class, but that becomes a little bit of a problem if you make it abstract, because if dog implements extends from animal, and because we don't have multiple inheritance, we're going to have a little bit of a problem in Java. So we'll avoid that, but though that's a really good idea, we'll avoid that for that reason for just a minute. And then what we will do here is, now that we wrote this friendable implementation over here, let's go to the human class. And let's go ahead and define over here a friendable implementation. We'll call it as friendable, or we'll call it friendable. And then we will say equals new friendable implementation. And then within this, all that we are doing really is, we'll do it first, and then we'll talk about what we just did. So we implemented that right here in the human, and then we are going to implement that right here in the dog class as well. Clearly, we could go the route of abstract base class to remove that duplication, if you will. But if you really look at this concept right here, the one I'm highlighting, we know it is not inheritance, but there's another name for it. Anybody remembers what that is called? The D word. That's correct, the delegation. Well, the code worked, and if this listen was a little bit more complex, we ended up reusing. So let's think about this code for a second. If I were to show you another example where we had a similar problem, we probably will end up with a very similar design like this. So you can see a pattern emerge out here. An interface and a class which has an implementation, most likely an abstract class if you will. And then we are delegating. So what is the pattern? The pattern is you inherit from an interface and then you delegate to an implementation. Well, if this is the pattern we're going to program, why in the world are we programming it? So if you really think about it, when you look at design patterns, design pattern is a sign of a weakness in a language. The more patterns you have, the weaker the language is. When a pattern becomes, when a language becomes really rich, the patterns become the syntax in the language and the idioms in the language, and you don't sit around and talk about patterns in that case, you talk about features in the language. When a language ends up lacking certain capability, we compensate for that using design patterns. So in this case, the pattern here is we implement an interface and delegate to an implementation. But if this is the way we're going to be writing code, why can't the compiler do this for us automatically so we don't have to be writing this code over and over and over? Well, that's exactly what a trait is. So a trait is simply a compiler implementation of the pattern we just saw here. So let's go ahead and try to see how a trait is going to look like. So what I'm going to do here is we're going to switch over. So we saw some solutions in Java, and what if the compiler can do that for us so we don't have to do this manually all by ourselves? That's exactly what traits are. So I'm going to look at traits. Anybody interested or using Scala here? Oh, that's great. What about Groovy? That's awesome. So I'm going to show you code in both of those languages, almost back and forth. We'll look at it. So I'm going to show Scala code right here on this window, and I'm going to show Groovy code here. I'll back and forth. I'll switch over, and we'll take a look at both of those. So let's say over here, we're going to have a class called human, and the class human, this is Scala code. So I'm going to say over here, name, and let's say this is going to be a string. And in here is the listen method, and I'm going to simply say print line. Let's go ahead and say over here, I am, and let's put the name over here, and we'll say listening. So in this example, as you can see, I'm going to create Sam equals new human. We'll create Sam, and I'm going to provide a seek help from, and this case I say this is going to be a friend, let's say human over here. And now that I have this object, I'm going to simply say in here, friend.listen and call the method right there. So let's go ahead and pass seek help from human, and let's pass Sam over here. So basically I have the code exactly like we started out in Java. I created a human class, implemented the listen method in it, and now we introduce our really good friend, dog. What do we do with the dog in this case? So I'm going to create a class called dog over here. And when I create a class called dog, once again, let's go ahead and say that the name in this case, that a dog has a name. You could have a different implementation if you wanted to, but let's say we're going to simply reuse it. And I'm going to have exactly the same implementation here in the dog class as well. Just like in Java, we duplicated that in here. But then I want to say buddy equals new dog, and this is going to be buddy, but I cannot simply pass the object buddy to this particular class because buddy is not a human, whereas the seek help from is expecting a human. So I'm going to change it to a friend right here. Now, once I declare a friend, notice what I'm going to do. I'm going to remove this method called listen from the dog, and I'm going to remove it from the human as well. So we got rid of that from both of these classes. But then I said trait friend, not friendable, just friend, and I'm going to define a listen method right here. But notice this listen method is using something called a name. So I'm going to say val name, which is a string. Now, for those of us who program in Scala, you know that you cannot define a val and walk away. You are required to provide a value for a val because a val is immutable. Well, that rule doesn't apply when the val belongs to a trait. So in this case, I just declared a val name as string, but I haven't given it a value. Where does this come from? It comes from when the trait gets mixed into a particular class. For example, extends friend right here, and then I'm going to say extends friend right here as well. And now you can see in this particular case, we have this particular object, and in this particular object, you can see that I was able to pass both human Sam and buddy the dog to this method called seek help from friend, where seek help from friend was taking a friend. But in this point, we have written a trait called a friend, implemented the listen method in the trait. We did not have the name defined in the trait. We just declared it. The value has not been given to it yet. And then in the human class, we extended the trait. And in this case, the word extends really is used to say you are mixing in the trait. This is not like an extension, like a class extension, but this is more like extending from an abstract base class if at all, but it really is saying that I'm mixing in this trait over here. Now you can see in this case, the name that you have here comes from here. If you were to call this something other than the name, for example, name 1, you will get an error because the name has not been implemented. So if you look at the error message in this case, it says class human needs to be abstract since value name in the trait friend of type string is not defined. Well, that's probably one of the most clearest error messages I've ever seen. It simply tells you what the problem is because we want to implement the name, as you can see in this case. So we implemented this, but it's good to see what really happened over here. Before we take a look at Groovy code, let's take a look at what's really happening over here. So I'm going to go to the command prompt here. So I'm going to see if we can compile and play with this just a little bit. So let's go back to this code. Let's go to where I have the Scala code sitting here. And right here, I only have this class file, which is sample.scala. But before we go any further, let me quietly comment out this for a second. And let's come back here. And this is the sample.scala file you're just looking at on the other window. So that's what I have on my hand. Now Scala C, and I'm going to compile the code over here and see what it provides. Let me get rid of this also for a second. Let's deal with the classes for a second. So let's compile this, and now you can see that it produced a bunch of files for us. Let's take just a couple of minutes to examine this so we can understand what's really going on. So if you look at the dog class and the human class, we'll come back to those in just a second. Let's look at the friend class first of all. So what is a trait, first of all, in Scala? Well, a trait trait, the minute you define a trait, let's understand what's really going on. Well, traits often run a buy one and get one free offer. So if you use a trait, you get an interface and a class right away. And that is why you get both of those things quite easily. So if you notice, we created a trait called friend. So let's go back and say Java P minus C, and I've already put minus C as an option on my alias in my machine. Let's look for the friend.class and examine what it contains. Now, if you look at the friend.class, you will notice that in this particular case, it created an abstract class called the friend$class right here, which contains the listen method. So literally they created an abstract class for us, which was a suggestion made earlier when we were talking about Java. Someone said, hey, why don't you do an abstract class? Well, that's exactly what Scala has done here. It's created an abstract class from it. So you can see that sitting right here, and that's the implementation of that particular method, the method called listen, that is sitting right here, as you can see. Well, in addition to that, they have an initializer as well. So you can see that they created an abstract class for us. If you look for the friend and look for the other implementation over here, the $class that is sitting here, let's take a look at this and notice that this is again the abstract friend class, the static listen method sitting here. And essentially what they have done is they have created a class for us to work with, and there is a hidden interface behind this for us to use in the case of an interface. So that is basically what a friend ended up being. But if I look at the class human on the other hand, if I look at the class human, Java P, and look for what human contains, well, notice the human implements friend. That is the interface I was talking about. So it implements the friend interface, and then it's got the listen method in here. But what does the listen method do? Notice the listen method routes this as a static method in the abstract base class. So in the example I wrote in Java, I created an instance and I delegated to this. These guys smartly delegate to a static method, and because it's abstract, you cannot create an instance of it, but you're routing it to the static method. That's basically what they're doing. So what are they doing in a sense? They're doing exactly what we did by hand, which is implement an interface and delegate the method to another implementation, right? So whatever we were doing manually is exactly what trait is doing automatically for us, so we don't have to waste our time and effort. But don't get me wrong, that's not all what traits provide. That's the first thing that trait provides, but we're going to build up on it and then see how much more powerful trait becomes moving forward from there. But that's the first thing that a trait is doing. So it implements the interface friend, and it then routes the call to or delegates to the static method listen in the abstract class for friend. That's basically what human is doing. And it would be no surprise to see that that's exactly what dog is doing as well. You can see the dog implements from friend and then has a routing of that call listen to the abstract method, to the listen method, static method of the abstract class. So that shows us how the traits are implemented under the hood. When we go back and implement this, we can see the power that this provides for us. I'm going to blow away my class files here, so let's get rid of those. All right, so we saw how that works in this particular case, what's under the hood. So essentially, at the very first side, what do traits provide? Traits solve this problem of where two independent abstractions end up sharing a common functionality. So traits provide this pattern of implementing an interface and routing to this particular abstract class. So we don't have to be writing any code for it. All you do is just declare it as a trait with an implementation. Keep in mind, a trait is a buy one, get one free. You got a class backed by an interface. Both of those are created for you. And anytime you bring in a trait or mix in a trait into a class, automatically you have this inheriting from the interface and routing to this particular method happen for you. The compiler generate this automatically for you. I showed this to you in Scala. Let's quickly take a look at this in Groovy. So trait over here, and I'm going to say friend, if you will, and define listen. And this method is going to simply say print line, and I am, let's say, name. listening. So this is going to be the listening method in the friend, and a class human. Let's go ahead and say human. And in this case, I'm going to say a string, let's say name over here, human, the name, and I'm going to set the name equals, let's say, equals the name. And now I want to create a method, let's say seek help from a friend, and I don't care to define the type. If you define the type, that's perfectly fine as well. And a friend dot listen over here, and I'm going to create over here Sam equals new human. We'll say Sam, and I'm going to seek help from, and then send Sam over. Now in this case, of course, it fails because we haven't done anything with the listen method. So now I'm going to say implements friend, and you can see that works fine. In the case of the Groovy, Scala uses the word extends, Groovy uses the word implements. Now, neither one of them is perfect in my opinion. I would have preferred something totally different, so it is very clear that we are mixing in a trait, but Scala chose to use the word extends because it naturally becomes you have a class name followed by extends. That's great. In this case, they said, oh, let's just pretend that traits are just interfaces, because in reality, they are interfaces, except they are backed by an implementation. But the Groovy compiler is smart enough to know that if you implement the interface, it simply says you abide by that contract. But if you implement a trait, then they do the magic we saw earlier, where they implement the interface and then do the delegation for you. All that is done by the compiler again in this particular case. So now if I create another class, in this case, let's say we create a class called dog. So in this case, I say dog over here, and let's say this is going to be the dog class. Once again, now we can say define buddy equals new dog, and then this is going to be buddy, and we can say buddy dot, let's say, actually seek help from, and then we can send buddy over here, and you can see that works as well. So that is the Groovy syntax for doing this. We're going to talk quite a bit more about traits as we move forward, but any questions or comments before we move on so far? Anything that intrigues you, or any suggestions, comments, just about anything? Yep, thank you. Go ahead.
The with keywords, I was thinking in the Scala.
Good. So stay with me for just a few minutes. We'll come back to with, and that's a bit of a confusion. But when you already have a, well, actually, let's talk about it. Let's talk about it. So if you look at this example here, in this case of Scala, let's say we have a class called animal. So I have a class called animal. Let's say name is going to be a string in the animal. Well, in this case, let's come back to using this in just a few minutes. So I'm going to only deal with the human for a second right now. So in this example, we only have the human working. Now the dog, let's say, is going to extend from animal. Well, for this, I'm going to say override, because the name is going to override from that, from the animal. And so this time we're going to pass the name over here to the base class. So now, if I were to call the buddy with this, we can see that that doesn't work anymore because the dog is not a friend yet. So to fix this, I cannot say extends one more time with friend right now, because we already have extended from the animal. We can't use extends twice. So I would have preferred consistency, but languages are not supposed to be consistent. That's one of the rules of programming languages, that you're not supposed to be consistent. So they had to use the word with here to get around that. So this is a bit of a anomaly in my view, in that if you are inheriting from a class already, you use with. If you're not inheriting from a class, then you use the word extends. So you can see the difference right here. So you can see that that works fine. On the other hand, if you do this, that works fine. So extends a class with a trait, or if you don't have a class to extend, then it extends the trait. So that's the way the syntax is. So you normally use a with if you already are extending an abstract class. Otherwise, you use extends to if that's your first trait. Yeah. Any other questions or comments? Yeah, please. So the question is, would it be possible to do this in Java 8 with default methods? Default methods somewhat scratches the surface. Unfortunately, the short answer is no. And the reason the answer is no is, we have come this far, you can get fairly close to up to here with default methods in Java, right? So what you could do in Java is, for example, let's go back to Java here for a second. We can say interface friendable, and to be fair, we could move this over here to the interface, and we could say default, and we could do this, right? So if you do this here, friendable, and now in fact, let's even call it as a friend. Let's elevate it to a good interface name. So interface friend and default method, in this case, listen, and we are implementing it right here. Well, that's great so far, but what about name though? Well, I don't want to pass a name as a parameter, certainly not. So what am I going to do in this case? I'm going to say, using the Java convention, we could easily say something like, over here, let's go ahead and say, call this as, what should we call this? Let's say this is going to be a string get name. So let's say this is going to be just a default method. Now what we can do in Java is we can say human implements friend. Well, now that we implemented the friend, we don't need these guys anymore, so we can quickly use that directly. We'll come back to the dog in just a second. So I'm going to go back over here. Let's make this a friend again. So this time around, I'm going to simply say that the human is going to implement that and bring it in here. Well, in this case, we need a get name method, which normally we provide, so I'm not complaining at all about this. So get name, and this is going to simply return the name value that you have on your hand. Well, obviously, for that reason, this is going to become a get name method, which is perfectly fine. So this aspect I really like. So notice how we got a get name. Well, that will be implemented by the implementer later, and the listen method can become your default method. That is awesome. Now you can go back and implement a dog similarly, and you can say this is going to be class dog, and then this is going to be a friend, and of course this is going to be the dog as well. And now we can come back and use the dog very nicely to do the same work. So looking at only this example, we may jump to the conclusion that Java has traits. Unfortunately, that similarity ends right here, because we're going to see more features in just a few minutes, and then to the extent that we are going to be able to do that in Scala and Groovy, we quite cannot get to that power in Java, at least not the way it is right now. So default methods are really not traits. It solves that problem we had, but it doesn't comprehensively solve all the problems that traits solve. So really good question. So that gives a little bit of a glimmer of hope, but it doesn't carry us way too far after this. So that there's limitations you will see in just a few minutes. Any other questions or comments? All right then, so let's talk about a few more things. We want to extend from the trait, and we did that. That's great. So we took the trait on our hand, and we said, I'm going to extend this trait and implement a certain features. That's great. But let's continue a little further with this. Notice how to the seek help method, we passed a friend as a human, and then in this case as a dog, and that worked just fine. But let's continue further a little bit. Let's say we have a class now that we have on our hand, and this class is going to be, let's call this class as the cat class. So we got a cat, and now I'm going to create alf equals new cat, and I'm going to create alf, and I'm going to say seek help from alf. Will this work? No, it won't work. Why not? Because cats are not friends, right? So in fact, you go home at the end of a very tiring day, the cat looks at you and says, why are you not still at work? Why are you here, right? Well, cats are kind of unique, but they don't show their friendship the way dogs show the friendship. So that is a lost cause. That doesn't really work. Well, that seems like it. Cats are not friends. Anybody with a cat over here? Oh, quite a few people. You, sir. Is your cat friendly to you? How do you tell him he's in denial? What's your name, sir? Daniel? All right, so would you like to share your cat's name with us? You forgot your cat's name? Complicated name?
Rebecca and Tiffy.
You get two cats. Oh, okay. All right, let's try this. I'm not promising anything to you, but we'll try. So, you said Rebecca? Equals new cat. Maybe with such a wonderful name. Maybe, I'm not sure. So, seek help from. Well, sorry, we tried. So, but he seems like he's really optimistic. Are you convinced they are friendly? He seems like, well, okay. So, what about this? So, this can be, well, cats are not friendly, but Rebecca is special, right? So, he's happy. Look at his smile, right? He's pretty happy. So, the point really is, in this particular example, actually, this cat is one of its kind, and I'm sure he will agree with it, right? So this is actually an anonymous inner class. If you really look for the type of the object, so if you say print line and ask for get class over here, and actually let's try something a little different. Let's go back here, and before calling the friend, let's go ahead and say print line friend.getClass, just for the sake of exploring. Well, notice in all of these cases, we got a bunch of anonymous inner classes. So let's get out of this. Let's actually try this outside so that it gives us a little bit more clarity on our hand. So if I go back here and say, let's ask for print line, let's say sam.getClass. So this is going to be about Sam. And you can see that it's a human, object of human, right? Keep that in mind. So then I say print line buddy.getClass. And you can see that it's an object of dog, absolutely. But then I say print line for Rebecca.getClass. And let's see what that tells us now. And notice that it is actually doesn't say cat. It actually says anon $1, and that shows that this actually is anonymous inner class that was actually created on the fly in this case, well actually during compile time, but on the fly over here. And the point really is, cats are not friendly, but this particular instance of the cat is actually friendly. So you can actually do this at an instance level rather than at the class level. Much like that in the case of Groovy, if you will. In the case of Groovy, let's go back here and create a class called cat. And the cat is going to have a name over here, and I'm going to say cat the name, and let's go ahead and say name is equal to, let's give this the name. Now if I come back over here to the code, and I define alf equals new cat, and we pass alf to this method, you can see in this case it's going to break because alf is not friendly. However, if I go back and say define and create a friendly cat, right, equals new cat, and so let's say in this particular case, let's say call seek help and pass the object, but before that we'll say as and provide the trait, in this case friend, and you can see that's working. So that's Groovy syntax. You can pass a trait using as friend or as whatever trait it is, and it'll mix it. Traits in Groovy and in Scala are compile time. So right at compile time, it's going to mix this in, and that's how it's going to make this as an implementation of the trait. So this is a compile time initiative. That's what you're seeing in this particular case. So you can do this not only at the class level, you can bring this in the instance level as well. Well, that's great so far, but what if I have multiple traits I want to bring in? Well, let's go back to cats for a minute. Well, some cats are friendly, but other cats are not. That's great. But there is one thing we can all agree about cats, right? They are very curious. So you want to bring in the curiosity into a cat, but we also know that dogs can be curious as well. And so how do we say that both dogs and cats are curious? And of course, some humans are curious too. So in this case, how do we bring the curiosity in? So notice what I'm going to do. I'm going to say trait curious, And now I'm going to say define, let's say poke around. And the poke around method simply says print line and we'll say curious. And so we have a curious method right here. So curious. And so we can see the curiosity can be brought in. But how do I bring it into the classes? So notice back here in the dog class, well, let's go ahead and say buddy, first of all, buddy here, dot poke around. So I'm calling the poke around method, and that's going to fail. And the reason it's going to fail, let me fix this compilation error here. This is Scala code. It requires a parentheses at this point. So notice it fails on poke around. Why? Because a dog doesn't have a poke around method. But what I'm going to do here is I'm going to say with, and this is going to be curious. And you can see that we are able to bring in additional trait into the dog. So you say with friend with curious, and that brings in that into the dog class. Likewise, we can go to the class cat, and of course you could argue all cats are curious, and in that case you would simply say with the curious right here for the cat, and you can see that in this particular case I can say our friendly cat, and I can say poke around, and you can see that has a curiosity in it too. However, just for proving the point here, if we say cats generally are not curious, but our friendly cat is also curious, then we can bring in with curious right there. So you can mix in multiple interfaces, traits rather, into an instance. You can also mix in multiple traits into a class as well. So you can do that with a with. Let's look at it in the Groovy side. So I'm going to go ahead and implement the curious over here. So trait curious, and in this case, curious. And in this case, let's go ahead and define poke around. And once again, in this method, I'll simply say, let's say curious. So curious. And once we write this little implementation, let's go to the dog, and we can say implements friend and curious. Now we can say buddy dot poke around, and in this particular case you can see that the curiosity came to the dog as well, because we said implements friend and implements curious. On the other hand, if you look at the cat, once again you could do this in the class level, but if you want to do it here, you would have to change this just a little bit. You can go and say with the trait, and then you're going to specify the friend, and you can also specify over here the curious as well. And now you can simply say that the friendly cat can poke around as well because it's very curious. So that shows you how you can use a with the trait in the case of Groovy and bring in multiple traits into a class as well. So this shows you an example of how you can bring in multiple traits into a class. But this leads us to a next issue, and that is, what if we have common methods in multiple traits, methods with the same name and same signature? Now, this is one of the problems in multiple inheritance, right? What do multiple inheritance do? When classes have the same method, and if you bring those two as base class, they end up colliding. What if the interface methods get together and they decide to collaborate instead of collide? What would happen? Well, then it would be nice and fun to mix them together and work with them, isn't it? Well, let's take a look at how we can use chaining of interfaces in the case of Scala. Well, to understand this, I'm going to change the problem just a little bit. Let's create an abstract class, and the abstract class I'm going to create is called writer, and the writer has a method called write, which is going to take a message, which is a string, and that is basically what I have on an abstract writer. Imagine I can have different kinds of writers, string writer, file writer, socket writer, whatever writer I could have, encryption writer, whatever, right? So let's create a class called, let's create this as a string writer, so string writer, and the string writer is going to extend from the writer interface. So I'm going to say define over here a target, and target is equal to, let's say, new string builder. So I got a string builder on my hand. Let's also override the toString method, where the toString method simply returns target.toString. And finally, so this is going to be the override toString method. And finally, I'm going to say define write message. And this is going to take a string. And all I'm going to do here is simply say target.append. And let's go ahead and append the message given to us. So this is our little string writer class. Let's write a method write stuff. And in the write stuff, I'm going to pass a writer. We'll call it writer. And what am I going to do with this writer? Well, with this writer, let's go ahead and write something first of all. So writer.write, and I'm going to write these words, this is stupid. And then I'm going to print out just the writer itself. Well, if I were to call this, let's say write stuff, and to write stuff, I'm going to pass, let's say new string writer. So if I pass the string writer, it simply wrote this is stupid. So we could send other kind of writers to a file writer, for example. In that case, it would write this is stupid to the file writer. But let's say the problem changes on us. We are told that we have these different writers, but we want one feature. At times when we write, we want the content to be written all in lowercase or all in uppercase, let's say. But to write all in uppercase, we want to be able to use the same functionality, but sometimes you want to write in uppercase, sometimes you would just want to write the content as it is. Well, I'm tempted to write a method called toUppercase in the string writer, but then I have to write that in the file writer as well and socket writer. That's duplication of code. We don't want to go that route. But if I'm tempted to put that in the writer abstract class, that class is going to bloat up. And also, if I want to add a new functionality, I got to come back and change that abstract class, and soon that abstract class will become a monster. It will also end up failing the principle called the open-closed principle, because every time I want to add a new feature, I got to change the abstract class, and that's a burden we have to go through. Well, in order to avoid all of that, let's make use of a trait. So what I'm going to do here is I'm going to define a trait, and we'll call it as uppercase filter, and this extends from the writer. And let's stay right here to understand what's happening. Uppercase filter is a trait. The word extends here doesn't mean extends. The word extends here means that this trait can only be used or mixed into any class that already is a writer. So that is basically the constraint you are placing. So think of the word extends here as a constraint on the trait. This trait is not usable everywhere. This trait is only usable with the writers, right? That's a constraint you have placed on this. So now I'm going to define over here the method called write. And what is the method write going to do? The method write says, I am going to take a message on my hand, and I'm going to write this message. So message dot to uppercase. So in this case, it converts the case of the message to an uppercase. But where does this message really go? We got to find a target where to write this particular message. Well, the target really is a writer that you're going to attach to this particular uppercase filter. So to say that you use the word super.write and you specify this. The word super here, much like the word extends, in this case the word super doesn't mean super. It really means that you are forwarding and calling another object which you expect to find. In other words, when you mix traits, it really forms a very interesting structure. Now let's think about inheritance for a second. When you use inheritance, what's going to happen? You have a class, and you have a base class, and you have a base class, so you form a vertical hierarchy in inheritance. With traits, you form a horizontal hierarchy. In other words, think of these like a chain or a train of cars of train. So you have a cart, and they all form a link. So when you call a method, when you call a method on a trait, super means go ahead and call this method on the object to its left. So you can imagine these as forming a chain, and when you call a method, it calls the object to the left and the left and the left. So the super is actually object to its left. Now for this to work, unfortunately, you need to have a super, which is the object on the right side, which has the method called right. Now how do you emphasize that an object is required to have a certain method implementation? Well, you do that by using the word abstract. So that means that you expect this to be replaced and a different implementation to be available. Well, then you put the word override. Now this is a very deadly combination, but what this says is my method right here is the same as the writer's right method. That's the override over here. And the abstract here says the next guy in the chain is required to have that method as well. And that's a bit of a confusing set of keywords, but the combination of that is used to provide that kind of capability in here. So given this override that we have provided, so abstract override simply says that the combination of this is going to provide this to us. So given these two keywords in the combination, what are we going to do with it? Notice now what I can do. I can call write stuff new string writer, and I'm using the instance level enhancement in this case, right? So with uppercase filter, but notice the output in this case. It really took the word, converted to uppercase, took the uppercase result, forwarded using super to the original class instance, which is the string writer. So you can see the chaining happen already. So in this chain, the string writer is the target, and the uppercase filter has been attached to it to its right. And so when you call the method on the string writer, it does the conversion and forwards the result to the string writer, which then writes to the target itself. But likewise, we can include more of these filters. Let's go ahead and write one more filter here for us to work with. So the next filter, and then we can play with it and see how the chaining will work. Well, the next filter I'm going to write is going to again do a conversion or a transformation of the input. Now, what am I going to use over here? Well, this is actually based on a very sad story. I came to know that I'm actually a bad guy. How sad it is to know that you're actually bad. Well, I travel around a lot and I kind of work with people in our profession. So what do you expect? Sometimes we are brutally honest. So I was sitting at home, talking to my little boy, and I, apparently said something, but quietly he immediately got up sitting next to me. He ran away and he whispered something to my wife, and my wife is whispering back something to him, and I see my wife coming towards me, and I knew I was absolutely in trouble already. And my wife came to me and said, "Did you say a bad word to the child?" I said, "A bad word? Why would I say bad words to children? What are you saying?" And she leaned over and said, "Did you say the S word?" And I whispered back a S word and said, "You mean that?" She's like, "Not that S word. I know you won't say those things to kid. Did you say the word stupid?" I said, "Of course I said stupid." She's like, "You're saying it again in front of the children." I said, "What's wrong with saying stupid?" Well, she said, "You're not supposed to say stupid. I've been teaching the children good manners. They got to be polite to everybody. You don't call people stupid." I said, "How do I know? We call stupid all the time to each other, right, at work." So it's like, okay, I'll not say stupid anymore. So I had to hang my head in shame and say that I will not use those words. How hard it is, you can imagine that, right? So for that, I'm going to write a little filter called the profanity filter, right? And the profanity filter, and what does this profanity filter do? Boy, I can't get the word out of my mouth. What the profanity filter does is, it replaces the word stupid, let's say with the word, how about that, right? So it makes a replacement of the word right there. So we could now use a profanity filter. So write stuff, new string writer with profanity filter. And you can see in this case, it got rid of that word nicely. Now, where it really becomes exciting is, notice the word method write over here and the method write over here as well. So we got the method named write in both cases. So this is a good candidate for collision. What are we going to do to avoid this collision? Well, we don't have to do anything because it's already taken care, because we said forward down the chain. So if you notice over here, write stuff new string writer with uppercase filter and with profanity filter, notice when I run this code, it is all in uppercase, but it removed the word stupid really well. But the chaining happens from right to left. So it starts with the profanity filter, which strips the word out, sends it to uppercase filter, which converts the case, and then sends to the writer, which string writer, which writes to the target. Now, on the other hand, what if I were to say write stuff new string writer with profanity filter with uppercase filter? Now clearly in this case I swapped the two out. But if you notice the implementation that I had on line number 20, you can see that in this case it only removes the lowercase word stupid, not the uppercase word stupid. So as a result, if you notice in this example, the word stupid gets through, and the reason is we applied the uppercase first and the profanity filter came later. Well, don't worry about it. This is perfectly fine, because the other day I said stupid one more time and my son immediately wanted to complain to my wife, and she said, "Daddy is really upset right now, be quiet." So it's perfectly okay to scream stupid when you're really angry, and that is an example where this really models the domain as well. So this shows how we can nicely chain the traits together and provide this kind of implementation. So this is one of the nice things about trait. So to go back to the question the gentleman had earlier about default methods in Java, this is where you will see the difference. You quite get close to this kind of behavior yet in Java. Would be nice to have it, but not yet. So that is an example of how the traits actually work. We can do exactly the same thing again, but this time we can do this in case of Groovy, for example. So in the case of Groovy, we can implement a very similar concept. So let's say we have a class called string writer one more time, and I'm going to define target over here equals new string builder. And there's a bit of a difference here in the case of Groovy. We'll see what that is in a minute. So string to string, and I'm going to simply return over here target.toString. That's the result I want to return from here. And let's go ahead and define a write method, which takes a message over here, and target.append, and I'm going to append the message to this particular target. So define over here write stuff. Let's go ahead and say write stuff. And the write stuff in this case is going to take a writer, and I'm going to simply say writer.write. Once again, we'll say this is stupid, and let's go ahead and print out the writer itself, and let's go ahead and call write stuff, but this time around we'll call this with a new string writer. So essentially all we are doing in this case is simply using that one object. But I want to do the filtering like we did before. So write stuff, new string writer, and then I'm going to say as, in this case, uppercase filter. Now we know this already, that we can use multiple traits together. But in this example though, what we want is the chaining of the traits, not just the availability of the trait itself. So we're going to say trait uppercase filter, and this is going to be well actually, let's try without it, we'll come back to it. So I'm going to write in this case a method called string to string, and in this case the to string method, I'm going to say super.toString and call the method on the base object. Likewise, let's go ahead and write the write method where I'm going to take the message. And what am I going to do with this particular message? Well, message.toUppercase is essentially what we want to do, but we'll say super.write and pass this to the base class as well as a way to pass this around, and you can see how easily we were able to implement that. So once again, in the case of trait, we were able to readily call the super.write, and that forwards it and chains it. So trait simply forms the same basis of forwarding the call down the chain. Likewise, I'm going to go ahead and call the next one here, which is going to be trait, and let's call this as the profanity filter. So profanity filter, and in this case, of course, I'm going to say replace, and one more time we will say this is going to be the word that should be replaced by, let's say, this other word. So now if I were to go back here and say write stuff new string writer as the Profanity Filter. So once again, we are bringing in the trait into this, and you can see that's working. But what about mixing those two? So string writer, well, in this case, I'm going to say with traits, and I want to bring in the uppercase filter and the profanity filter all into one. Well, that's at least the goal. Unfortunately, that didn't quite work very well. It is giving us a compilation error. So I'm going to go ahead and move this here as inst1 and define inst1 equals, put that over there as a separate instance, and you can see that's working. So this seems to be more of a compiler issue where the compiler is just choking up when it sees this along with the context of the other call. So by moving it around, it seems to be just fine. So similarly, instance 2 equals new string writer, and then I'm going to, with traits this time, profanity filter and the uppercase filter, and then write stuff one more time, instance 2, and you can see in this particular case, the word is not removed because of the sequencing you see. So this shows us how we can use traits, and we can chain the traits together, and I simultaneously went through Groovy and Scala together, so I don't have to do that separately. So you can see the chaining happen nicely followed through. So that is basically how traits can actually collaborate, and to me, this is the feature I really like about traits, is that you are able to realize the power of multiple inheritance without the pain of multiple inheritance, and you are able to bring those implementations on Mixins. So I use the word Mixin, but we've been looking at traits, so what's the difference? Well, if you go to a nice ice cream shop, and if you go to a nice ice cream shop where they have ice creams, but then you have all these toppings that you can get. I know this is a really bad thing to talk about, right? So, but we kind of put on weight just by talking about ice creams. But nevertheless, you go to an ice cream shop, you know, I could get maybe a nice vanilla ice cream, put strawberries on it, almonds and cashews and peanuts, oh boy, on all of this, and load up with whipped cream and cherry on top. Wouldn't that be nice? Well, I've got a son, and I really am suspecting if he's a human or not, because he goes to the store, he would order a chocolate ice cream and will put chocolate chip on top of it for Mixins. So I don't know, weird, but that's the way he is wired. Anyway, so these are called Mixins, right? So you go to the ice cream shop and you can put Mixins. Well, what a nice flavor to enjoy. Well, that's exactly what we're doing when we program with traits. We are mixing in these concepts into our abstraction. Well, then why we call it trait versus mixin? So here's the way I understand it. The traits are compile time mixins, while mixins are runtime mixins. In the case of Groovy, we had compile time mixins. We have compile time mixins now, which are traits. Traits are relatively new in Groovy. I'm not really good at versions, so I apologize because my little brain doesn't hold version numbers, but it was released, a few months ago, whatever that version was, 2.38, whatever it is, I don't go with numbers. So in Groovy, traits are fairly recent. Mixins have been in Groovy for a while, but mixins have been implemented poorly in Groovy. So the idea moving forward is mixins would disappear and traits would become the replacement for mixins in Groovy. So if you're programming in Groovy, Scala doesn't quite have support at runtime for this. You have the traits, definitely. Groovy had mixins. I'm using the past tense had. You still have it, but it's better not to use them if you can. Move forward to using traits moving forward. But if you really want to look at a nice implementation of mixins, I encourage you to take a look at Ruby. And Ruby has a really wonderful implementation of mixins. What you do in Ruby is you can write a class and you can do an include, and when you do an include, it will mix that particular module or a class into your class. But what Ruby actually does is it forms this chain of objects like we talked about. So it'll have your object, then it'll create a little object with the method which will point over here, and then you can have all these nice chains of objects, and then you can have these forward the calls through. So very powerful object level detail. And not only can you do that, you can go insert into this chain and vary objects also. And Mixins can also become very powerful technique to use during meta programming in Ruby also. So you could try to enjoy Mixins through on the JVM through JRuby if you're interested. But Mixins are really very powerful in Ruby. But with Groovy itself, like I mentioned, it's better to move away from Mixins and start using traits. And one of the reasons I say this is, when I was writing the Programming Groovy second edition book, I ran into a problem with Mixins, and I found out that doing a nice chaining with Mixins was extremely painful. So I reported a bug saying, here is the amount of effort I had to put in to implement a Mixin. I think this is really horrible. It would be nice if you can change this to make it better. And the response I got was, well, it's not you, but we also hate Mixins. So no, we're going to reject your request. We will not change this. We're going to completely rework it. And of course, then after that, what I saw was trait coming out, and traits are doing a much better job than what Mixins did. So Mixins have certain rather limitations in Groovy, whereas traits have kind of fulfilled that and gone beyond it. There are a few rough edges still, but I think for most part they have done a fairly good job in terms of how they implement it. So to summarize what we talked about so far, we talked about how we can use traits to solve some very common problems. The common problem emerging out of multiple inheritance, in other words, our goal is to extend an abstraction using the features available from multiple abstractions. While default methods address this problem to a certain extent in Java, the real power is when we can take these abstractions and we can chain them through very nicely. And in order to be able to do that, traits and Mixins are really good solutions to make that kind of extensibility possible. And to make this extensibility possible, trait is nothing but a combination of an interface and an abstract base class. That is the two combination you get. Every time you write a trait, you get an interface and an abstract base class. And when you implement a trait, either using extends or implements, whatever the syntax may be, what you are really doing is, under the hood, you are implementing an interface and delegating the calls to this class, the abstract base class that you talked about. So that is how the routing actually happens through it, and so that captures the essence of that design. But moving forward from there, what traits really provide you nicely is the so-called chainability or stackability, depending on the term you are using. So you can nicely chain the traits, and when you make a call, the call can ripple through, and you can provide a combined effect. In other words, if you really think about this particular feature you saw, the chaining is really nothing but the decorator pattern, right? So the decorator pattern is not a pattern you implement specifically. It is what you do with traits in the case of Groovy and Scala. And so going back to what I mentioned earlier, we talk about patterns when a language doesn't have a feature. When a feature is in the language, we quietly use it, and we don't talk much about patterns, because using the language nicely becomes the pattern of usage at that point, rather than saying, oh, here's a pattern we should use because the language doesn't provide it for us. It becomes a feature of the language rather than a pattern that we have to use. So that's basically about traits and Mixins and how we can benefit from them. Any questions, comments before we wrap this up, please? What do I think about self-types in Scala? I think the minute I hear the word type, I'll tell you what I think about in Scala. There are a very small area of really powerful usage, but most of the time it makes programs unnecessarily and overly complex, in my opinion. And so, are they good ideas? I'm sure they are good ideas in a very small area of design, but I often find that people overly complicate things. So I tend to normally, use that and similar features very reluctantly. I want the features to be a lot more fluent and easier to understand and work with, and so that's one of the reasons why I'm not a huge fan of anything related to where we start messing with the type, and self definitely is one of them. I'm fairly reluctant in using some of those things. Other questions or comments, please?
Why did you override both two string methods in both traits in Groovy?
Right. So the question is, in the case of Groovy, so this is, I just kind of mentioned that there are some rough edges. So let's talk about some of the rough edges. And some of the rough edges are, if you look at Groovy, unfortunately, in the case of Groovy, if I don't write the toString method in the uppercase filter and I don't write it in the profanity filter, well, these two methods don't exist now in the trait. This is what I was talking about as rough edges. So notice what happened in this case. They end up providing the toString implementation rather than saying, hey, I'm a trait, I'm going to let it pass through. Those are some of the little rough edges I was talking about. It's a little annoying because you have to override those even though you have no real work to do at all. But unfortunately, the traits, the way they're implemented, is they are actually objects that are chained together, and they should be less of an object than they are right now. But in this case, they are saying, oh, you know what, I don't know whether you are connecting me or you're just using me here, so I'm going to provide those implementations for you. This is where the rough edge leaks through, because if you're not using chaining, but you simply did an implements, then you would not see the toString method because you're going through the object and you're mixing the trait in. But when you're doing a chaining, your entry point is through the trait and coming through the object, so that's where it begins to mess up. So that's where the rough edge is, where I kind of alluded to it and didn't talk about it. But the rough edge is how you bring in the trait and whether you treat it as an object with a trait or you're using the train and then going through the train to access it, and it's going to bleed out. I wish this was a lot more, hygienic, if you will, but that's some of the rough edges you're going to see in traits with Groovy. The 80% use case is really nice in Groovy, but the minute you're trying to do this for chaining purposes, it's not going to be very, it's going to be a little bit messy, like you saw. That's the observation you had right there. Good question. Any one more question, maybe? All right then. Well, why don't we take a break? Let's take a 30 minutes break. And when we come back, we're going to jump in and talk about monads and what do they mean. And I'll come up with some examples that we can maybe look at to understand what those things mean. Thank you.
Some people find it hard to see. Oh, yes, they do. Yes, they do. Yeah. But every time you look at me, no doubt about it, you and me, we got, can't stop it now, can't hold it down. If I needed to, I'd give it all up. Oh, don't ask for more, I'm living for. Oh, if you feel love, put your hands together like this, y'all. Put your hands together. Put your hands together like this, y'all. The way that I feel about you, girl, I wouldn't trade it. No, no, never. For all of the money in the world, 'cause I can feel it. You and me, we got, can't stop it now, can't hold it down. If I needed to, I'd give it all up. Oh, don't ask for more, I'm living for. Oh, if you feel love, put your hands together like this, y'all. Put your hands together like this, y'all. Now I wake up in the morning and feel you next to me. I know I'm blessed from above, 'cause it's all so clear to see that I got real love. Yes, I got real love. Can't stop me now, can't hold it down. If I needed to, I'd give it all up. Oh, don't ask for more, I'm living for. Oh, together like this, y'all. Put your hands together like this, y'all. Put your hands together like this, y'all. Put your hands together like this, y'all.
I remember just hanging around in the town where we grew up, having fun, acting like a clown, till our parents told us to stop. I'll treasure these moments for the rest of my days, and think of my friends in so many ways. Don't you know these are the good times, the times of our lives? Enjoy the good times that give us the drive to go on. The good times, not thinking about tomorrow or what may come. No, 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 no. tough, but that won't make us give up. 'Cause I feel like bubbles tonight, and the bottle's about to pop. 'Cause we should enjoy our happiness. 'Cause these are the times I don't want to miss. Don't you know these are the good times, the times of our lives. Enjoy the good times that give us the drive to go on. The good times, not thinking about tomorrow.
You're not that, you're not that, you're not that beautiful. You took the best of me, don't seem to need the rest of me. When will you realize that I'm still around? You've been ignoring me for quite a little, boring me, while you've been compromising all over town. Why would you think of making up? I guess you heard we're breaking up. Night after night I'm on my own, and now you're stalking me. Where did you get that attitude? I guess I'm just not in the mood. This is the end of the story for me. Come on now, why don't you get a clue? This love affair is through. All I can say to you is you're not that beautiful. Why would I wanna stay? I can't go on this way. All that I got to say is you're not that beautiful. Been working day and night, been trying hard to get it right, while all my needs and dreams get put on the shelf. Love ain't no 9 to 5, ain't gonna be your pretty wife if I don't get a little love for myself. Why would you think of making up? I guess you heard we're breaking up. Night after night I'm on my own, now you're stalking me. Where did you get that attitude? I guess I'm just not in the mood. This is the end of the story for me. Come on now, why don't you get a clue? This love affair is through. All I can say to you is you're not that beautiful. Why would I wanna stay? I can't go on this way. All that I got to say is you're not that beautiful. You're not that, you're not that, you're not that beautiful. You're not that, you're not that, you're not that beautiful. Why don't you get a clue? This love affair is through. All I can say to you is you're not that beautiful. Why would I wanna stay? I can't go on this way. All that I got to say is you're not that beautiful. Why don't you get a clue? This love affair is through. All I can say to you is you're not that beautiful. Why would I wanna stay? I can't go on this way. All that I got to say is you're not that beautiful.
All right, let's get started again. Welcome to the second part of this presentation. We're going to talk about monads. For those, if you joined just now, we talked about traits and mixins in the first part. In this part, we're going to talk about monads. And I'm going to talk about a little bit about functional programming and some of the reasons for looking at something like this, some of the challenges also, and then we will talk about monads. Well, the first question is, when we talk about programming, we are looking at a transition as we move forward from the way we've been programming to the way we would like to program. And one of them is in the area of functional programming. And so what is really functional programming? If you think about functional programming in a sense, functional programming is a way of programming where we treat functions as first-class citizens. And the benefit of doing that is, in Java especially, we're used to doing object composition, which means we create objects and we can pass objects to functions, we can create objects within functions, and we can return objects from functions. So we've been using function composition quite effectively. Object composition quite effectively, that is. But in addition to object composition, with languages like Java 8 now supporting functional style of programming, we can not only use object composition, we can mix and match function composition as well. And we can, in function composition, we can pass functions to functions, create functions within functions, and we can return function from functions. But what are some of the benefits of this kind of modeling? Well, with functions, we can express certain ideas as first-class citizens, and as a result, our program becomes a lot more expressive. If you think about something fairly simple in terms of how Java itself has evolved, let's take a really quick example to think about why functional style is so important. Let's look at a fairly simple example here for a minute. If I were to say thread, and let's say over here, equals new thread, this has been around for such a very long time, and then we could do something like, for example here, let's say in main. So this is, of course, running in main, but within this, I can say new runnable, and then we could say a public void run, and then we could output in another thread. So if we run this, we can see that in main ran, but in another thread is running in a separate thread. So you can see the outer sequence just to illustrate that those are in two different threads. But if you really look at this particular example, if I were to explain in words what I am trying to do here, those would be, I want to run that one line of code in another thread. Or in other words, we could even say, I want to run that body of code in another thread. Or we could go a little further and say, I want to run another function in another thread. So notice in all this discussion, we are saying, I want to do something with the function. But what did we do until recently? We told functions are not first-class citizen. We treated functions like kindergarten children, right? Functions say, can I go out to play in the park, please? No, sweetie, you cannot go alone. You need a little adult to take you over there, right? And so we wrapped it into an object. And functions have been feeling really terrible all these years, right? And it's like, can I go out? No, you cannot go out. We got to send somebody with you, right? So now functions are first-class citizens. Notice what I can do now. I can simply remove the object, only take the function, nothing else, and I can simply send just that function alone. So finally, functions have gotten the respect they deserve in Java, that they can be treated as first-class citizens. So we took this one function and said, here we want to send this function over and run this in a separate thread in this particular example. So by modeling with functions, we can be really more expressive. So that is one of the biggest benefits we see. However, one of the key things about functional programming is they honor immutability. In other words, they say it's assignmentless programming. Now, wait a minute, how could you program with no assignments? Well, to understand what it means to program with no assignments, let's look at a slightly different example. If you remember good old Dijkstra, Edgar Dijkstra wrote this phenomenal paper that said go-tos are evil. And he said, it's really bad to use go-tos. In structured programming, we don't use go-tos, he said. Well, that's great. We shouldn't use go-tos. In fact, in Java, go-to is a forbidden keyword. In fact, if you notice, if I were to say blah over here, and if I run the code, notice the error is not a statement. That's what it says, right? But if I use the word go-to and do the same thing, it says illegal start of expression. Notice the error is not the same. So something funky is going on here, isn't it? Well, it turns out go-to actually is a forbidden keyword, meaning it's a keyword, but they threaten to burn your village if you use it, right? So you're not supposed to use it. That's where the difference is. However, notice that if I say for, let's say int I equal to 0, I less than, let's say 5, I plus plus, and then in this case, let's say simply print the value of I, just a little loop, that's all I have, right? Nothing really complex. However, if I go back to the command prompt for a second, let's go to where this code is sitting, and let's take a look at Java P and -C is an option I already have configured on this machine, and look at the sample code that we just wrote. Well, surprise, notice what you see at the bytecode level. Well, you see go-to. So the point I want to make is this. We're not supposed to use go-to, but that doesn't mean there is no go-to. Go-to happens under the hood in a controlled manner, as you can see in this case. So just like you and I don't use go-to, but go-to happens under the hood in structured programming, in functional programming, you and I don't use assignments, but assignment happens under the hood in a controlled manner. But having said that, now that we're not going to do assignments, what is the benefit? Well, the benefit is we want to create functions with no side effect. Now, what would be some of the benefits of creating functions with no side effect? Well, first of all, what does it mean functions have no side effect? Well, a side effect means when you execute a function, it's going to change a certain things in its context around it. It could be an external variable, it could be a variable given to you, and so on. Let's think about this for a second. If you were to be in Java, let's say we have a function, and I'm going to say public, let's say static void foo int a, and I'm going to output the value of a. You could call foo, let's say, with the value of 4, and you can see that the value of 4 got printed. But what if I say, maybe there's a lot of different lines of code right here, and then right along the way, somewhere in the middle, I decided a equals 7, and I modified it. Well, you can see that the variable that was passed in as a parameter, we modified the variable right in this code. Now, this is mutability. Clearly, we are mutating a variable. It could be even worse. This could be a reference to an object we received, and you could modify the state of the object. Now, what's wrong with programming like this? I remember one day a programmer came to me and he said, here's a function I wrote, and to his credit, it was only about 20 lines of code. It's not like he wrote a monstrous 7,000 lines long method, right? It was only 20 lines of code. And he came to me and he said, here's a function I wrote, and for the life of me, I cannot figure out why this function produces the wrong result. And both of us sitting with it, looking like idiots going through to find out why this function is producing the wrong result. And I said, if you send 22 as an input, this should be the output, right? He's like, yeah, correct. But it is not. It is something else. So we're scratching our head. And then we start stepping through every line. And suddenly we realized on line number 7, he's actually modifying the input parameter given to him. And I said, are you seriously modifying the input parameter? And as soon as I said it, he's like, duh, I know what the problem is, never mind, and walks away, right? So we are in denial that we could actually modify input parameters. Well, from the language design point of view, let's talk about about this with another example here. Let's say we are programming in Scala. I have this function called foo, and I said over here int over very similar to what we saw in the case of Java, and I'm going to call foo with the value of 4 again, and notice in this time it really prints the value of 4 as we saw. But once again, let's say we have a number of lines of code over here, just like in the Java side, and I'm going to come in and say a equals 7 over here, and notice right off the bat, the compiler immediately complains to us. And the Scala compiler says, are you serious? You're trying to modify the input variable? So the compiler acts extremely surprised that I would even dare to think about changing input variable, right? And the reason for that is, Scala considers all the parameters as final already. You cannot modify it. The other day somebody was asking, hey, neat, this is great. You cannot change input parameter, but if I really want to, can I do it? And the answer is yes, go back and program in Java, right? So the point is, no, you cannot, and the language has the right attitude, and it's very opinionated, as people say, right? So that's basically built into the language. But mutability is something we should really care about. Now, to be fair though, in Scala, how do you create an immutable variable? You say val x equals 22, and then you can print the value of x. For example, you can see it is x, but if you say x equals 17, the compiler immediately screams at you and says, dare not, you cannot change this. Well, unfortunately though, Scala is not a pure functional language. You can actually mark variables as var, and then you can modify the variables though. Now, what is var? Var is called the keyword of shame in Scala. So every time you use it, you got to hang your head, in shame, because you're creating mutable variables. But the language does give you that ability to create mutable variables. But if you create functions with no side effect, there are some really big benefits that you have. For example, when you have a function with no side effect, what it means is, while this function is running, it doesn't sneak around and modify a global variable or a variable outside. And at the same time, when the function is running, it doesn't modify the input given to it, or it doesn't send you an output and then create a thread and with vengeance comes and modifies that variable, right? Those are very scary code people often write, where they give you a result, but there's another thread waiting to modify that object. Very difficult to debug, and errors happen. So a function with no side effect does not modify any state when it's running. Now, a function with no side effect is easy to test. And the reason is, no matter how many times you call this method with exactly the same input, the output is going to be exactly the same over and over and over. So as a result, if you give a certain set of input, you're guaranteed the output is going to be exactly the same. So as a result, there are some really nice benefits we are going to get into. Let's look at some examples here for a minute. Let's say I have a method called add with operation 1 int and operation 2 int, and now I'm going to say in this case the result is this operation 1 plus an operand 2. Now if I were to call this, let's say call with 1 and 2, and you can see that in this case it gave us a result of 3. And I'm going to do this a few more times, and you can see that it's going to be exactly the same result. However, if add is a pure function, and guess what? We know that add is a pure function. How is add a pure function? Because you give it 2 input, it doesn't mess with these 2 input. We already saw that. Scala doesn't allow you to modify the input parameter. Even if it's a reference, if this is an immutable object, you cannot modify the value in that reference. So, and then when you do a computation, it simply returns the result to you. As a result, this is very, very pure. Well, if it is very pure like this, a compiler can look at this and say, hey, I've got an idea. Let's go ahead and say, in this case, I'm going to replace this with something along these lines. I could say result equals add 1 comma 2, and then the compiler can say, I'm going to replace this with result, but I notice that you're calling add again, but the result is 1 and 2 another time, so I'm going to change it to a result as well. And so the compiler can perform optimizations where it can remove multiple calls to the function and replace it with the result from a previous call. This particular capability is called a referential transparency. And referential transparency has some really, really powerful advantages. The first advantage is a compiler can perform quite a number of optimization when it knows that functions are pure. It can replace a function call with the value of a function previously called. So this can be extremely powerful. Not only can it do this, there are concepts that like memoization. So another wonderful feature is called memoization. Now, what in the world is memoization? Well, let's take an example for a minute. If I were to ask you to perform a computation and you take the time to compute and you give me a result. Now, if I ask you to perform the same computation another time and you quickly realize the input parameters I'm giving you is exactly the same, what are you going to do? You're probably going to return the value from your memory, right? Now, we call this caching, and everybody knows what caching is. Because everybody knows what caching is, they cannot call it caching. They got to give a name that nobody will understand. So they called it memoization. So what is memoization? It's caching. So essentially the idea is when a function is pure, you can do some really fantastic capabilities with it. So if a function is pure, you can say, call the function, first of all, when you first call it, store the result, return the result. Well, the next time you call the function, if a result already present, then let's say the result is not already present, so we'll say not already present, then you call the function and you store the result at this point, and then you return the result. So now you can see the pseudocode. If the result is already present, you simply return the result. If the result is not already present, then you call the function and you store the result and then you return it. This is only possible if the function is a pure function. If the function is not pure function, you cannot use memoization, because every time you call, the result may be different and there's no point storing the value. You got to recompute because it is impure. Now, memoization is another benefit. Another benefit of pure functions is parallelization. Now, let's understand what the benefit could be. Imagine for a minute, I've got two functions with me. Here is function 1 and here is function 2. And imagine I don't really care about the results of either one of these functions right now. I really need them much later on in the time. So I could be doing something along these lines, right? I could be doing something like we have an add, I could have a subtract method over here, and so this could be subtract, and what I could be doing is I have some bunch of values, so we could say val, let's say v1 equals 4 and val v2 equals 7, and I could be doing add of v1 and v2, and this could be result 1, for example. Then I could be doing val of result 2 equals subtract, let's say v1 and v2, and then further down below I could be doing something like result 1 plus result 2, let's say, for example. So if I run this code, we can see the result is 8. Well, that's great so far. So in this case, when I run this code, the compiler could say, oh, you know what? You don't really need the result of each other until later time. And I'm going to run function 1 first, and then I'm going to run function 2. So it runs in this order, function 1 and function 2, and performs this computation in this sequence. Well, that's great. But the compiler can also say, you know, I realize that I have some data already in the registers, so it is much more performant, easy to do this. I'm going to run function 2 first, and then I'm going to run function 1. So the compiler can decide to change the order of this function. Now think about this for a minute. If this function was impure, can the compiler do this kind of change? The answer is absolutely no, right? Because if this was impure, calling this is going to leave some residue, and potentially this is going to access it because this is impure too. So as a result, we cannot change the ordering. But if these two functions are very pure, the compiler can run it this way or it can run it this way. Much like in this particular example, I can say the result is 8, but I can simply say I want to do them in the reverse sequence and the result is still the same. same. It didn't matter which order in which we evaluated. On the same token, we could also say, well, the JIT compiler in this case, because the JIT compiler knows about the hardware on which it is running, and the JIT compiler comes along and says, I got function 1 and function 2, I could run them in this order, I could run them in this order, or I realize that I have multiple cores available, I'm going to actually run them concurrently. So parallelization is easier when functions are pure as well, and so functional programming promotes easy parallelization due to purity of functions. So as a result, I could put these two in two different threads, for example, and run these two. Of course, add and subtract are so trivial, I wouldn't dare to put them in multiple threads, but if these were computationally expensive calculations, I could put them in multiple threads at the same time, have them execute concurrently, and get the result and move forward. So parallelization becomes easier to provide as well with purity. So purity gives the benefit of easy to understand, fewer errors, and also it becomes easy to parallelize the code. It's easier to use techniques like memoization, referential transparency, optimization by compiler. So the collective good of purity is really is big, and every one of them can come together. Well, that's all great, and we talked about the benefits of purity and what we can do with it. But then you say, okay, this is great, however, what does it mean when a language is absolutely pure? Well, you go to the guys programming in pure functional language and you ask them, do you write code where nothing ever changes? And those people tell us, absolutely, we write code where nothing ever changes. And you say, no mutation at all? Absolutely not. New impurity at all? Absolutely not. And then look at them and say, what do you guys smoke? Right? How could you write an application where nothing ever changes? Actually, it's very easy to write code where nothing ever changes. You can actually do this in Java too, if you didn't realize it. So I'll show you an example. This code is absolutely pure. Nothing ever changes, right? But it doesn't do anything for us, but that's a small problem, right? But this is like nirvana. We obtain this purity ultimately, right? So how do you ever write code where nothing ever changes? Well, that's where the little secret is. They say everything is pure, but we use monads. And these guys are very clever. They say it because nobody has a clue what they're talking about, right? So what in the world does monads mean in that context? So here's my take on monads. Monads is a way to introduce impurity in a world which is otherwise pure. Now, it is very difficult to really see what this all is big deal about it because of where we live. We live in Java, right? Most of us do here, right? We live in Java. And that to me is like living in the bazaar near the slum. And everything is happening there, right? We mutate stuff, and I love living there, don't get me wrong. It is fun because there is busyness. Everything is happening, and you can just sit there. There's not a boring day for us, right? But that's where we live. And then these guys programming functional programming, they live in this place called Narnia, where everything is so pristine and beautiful, and I could never find where that wardrobe is so I can walk through to Narnia, right? So it's really hard for me to sit here in Java and even think of what this would actually mean. So if you would permit me, let me deviate from Java for a minute. Is that okay for you? And just get a feel for what they actually are talking about. So let's go over here just for a minute or two, and I'm going to write code a little bit in Haskell here. So I'm going to write a method called add op1 and op2 equals op1 plus op2. Now notice right there, we have a pure function, right? This function is absolutely pure. Nothing is happening in this function that is going to mutate stuff. I'm going to come up with the REPL here, and I'm going to do the same thing. Add op1 op2 equals op1 plus op2. So in this particular case, all I have written is just a function. That's all I have written, nothing really else, right? Now that I've written the function, let's call add 1 and 2, and you can see it produced the value of 3. That's great, right? But I kind of chickened out in this point. I just wrote this function. We were able to see the result here in the REPL. But if I go back to the code, how do I get the result? One of the things I do is I teach remotely at the university. And yesterday there was an interesting email from one of my students. He said, okay, I don't get it. I've written program in multiple languages. And secretly one of the things I do is I put a little print statement in functions to see what they're doing. Now I'm programming in Haskell. And man, it gets angry if I put a print statement. What's going on here, right? So it can be really shocking for us to think about it from other languages' point of view. So if I were to do something along these lines, let's say I come to this function here for a minute, and I'm going to say over here, print line op1. I'm just trying to print it, let's say. Notice how mad it just turned into. It's complaining. Now, what in the world is it saying? It says couldn't match blah, 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 and actual type is IO parentheses. Now, what does that really mean? I want you to think of the letters IO as nothing really fancy. The way I look at IO is a little annotation for impure operation. How about that, right? So IO means impure operation. So in other words, I look at it as an annotation, meaning if you are pure, don't tell me anything. But if you want to be impure, this is like children. Can I go to the bathroom, please? And you get a little token to go around in the corridor, right? So it's like that. It's a little annotation to say, in here, I want to be impure, please. And so once you do it, you get a little authorized impurity on your hand. So if you want to look at it, how that's going to look like, just as an example, let's say main equals, and I'm going to say print line, add 1 and 2, and this is basically the output 2. But if you want to go ahead and call this one more time, for example, and print it, hey, what's wrong with this? Now it complained to me I cannot call this again. So notice what happened. It's embalming on me. Why? What's the reason for it? Well, the reason for it is, look at main for just a minute, if you will, and let's go back and run this one more time. So look at this particular example that we have in front of us. Let us say I have 1 and 2 add and 5 and 4 add. Now, if you look at lines 4 and 5, by default, what did we just tell Haskell? We said add and add are pure, which means it can run line 4 and run line 5, or it can run line 5 and run line 4, or it can even run both of them exactly at the same time in parallel. Well, that is the default mode in Haskell. And the reason I mention it is very difficult for us to realize this in Java, Scala. Every single language on the JVM has this problem. Because in JVM languages, we know one thing for sure, right? In JVM languages, if you say something like add 1, 2 and add 4, 5, you know very well that line 4 finishes before line 5 starts. The first call to add is done first, and the second call to add works later. In other words, in imperative languages, and most of us programming on the JVM have only programmed in imperative languages. In imperative languages, statements imply sequence, not in languages that are purely functional. In purely functional languages like Haskell, the sequence, the expressions you have written do not imply the sequence. So in this case, there is no implication of sequence. 4 and 5 can run in any order whatsoever. Am I making sense? Now, because of that, when I run this code, notice Scala got very angry. And what is the problem with Scala's anger? It says, well, you cannot run those, especially when you have a print statement, for example, right? It says you cannot do that. Why not? Well, the reason for that is you really need to impose ordering on the print statements. If you are running this program, you would be very angry if the output at all is messed up, right? When you produce output, you don't tell tell the user calls you and says, why is all this output messed up in random order? And you don't say, that's because we write in functional programming. The users are not going to be kind to you, right? That's called dysfunctional output. And you don't want that. You want them to be in the right sequence. Well, in order to do this, what you have to do in case of languages like Scala is, Haskell is, you got to put a little annotation to say, do them sequentially one after another. In other words, by using the word do, you are literally turning off the compiler's capability to apply referential transparency, because referential transparency is the default in a purely functional programming language. That's why I call this Narnia, because we don't feel this when we program in Java, because in Java it's imperative. The sequence of expressions we write is the sequence in which they are evaluated. That's not the case in languages like Haskell. So that is an example of what we have to be careful with. And because there are no side effects at all, how do purely functional programming languages really cause side effect? Now, what are some of the side effects we have to be careful with? Well, things like, how do you read from a terminal and a file and a database? That is an impure operation, isn't it? Because if I'm entering data, I could be entering a different data each time you run the program, which means that function is no longer pure, because every time you run that function, if it reads from a terminal, its behavior will be different. So no longer can we say, every time you run this code with no input, its output will be the same. Not really, because it is taking input from the terminal or a file or a database. And similarly, if you're writing to the output, you could be writing to a console, to a file, to a database, and that is also impure. Why? Because as you're running it, you got to make sure that the sequence in which the output appears matters as well. So as a result, that's an impure operation. So reads are impure, writes are impure. Even the very fact that you want to know what the current time is, that is an impure operation. Because guess what? Every time you want the current time, it keeps changing, right? So as a result, it is impure operation as well, and that becomes a bit tricky. So let's talk about how could we really experience this. And I'm sorry, but it is really hard to show this in Scala. Well, I only said it's hard to show. I didn't say it's impossible to show. So we will make an attempt to kind of get a feel for how this actually feels in Scala. So in Scala, I'm going to say define get, let's say, input. And the get input function says, I'm going to read a value. So let's call it input equals stdin.read int. So I'm going to read an input. So scala.io. So I'm going to read an input. And once you read the input, I'm going to return the input over to you. And right there, I'm returning the value for you as an input from this particular case. Well, notice in this case, I'm going to read the value and return to you. So let's only return that. I don't have to say anything more. And let's say print line, something along the lines of, let's say enter int, right? Or enter a number. So this is going to be enter a number. Now remember in this case, if I said val input 1 equals get input, and I'm going to say val input 2 equals get input, and I'm going to print out input 1 minus input 2. Let's just take this example for a minute. Now remember in Scala, we know this already, right? Because by nature, Scala being a hybrid language supports both impure and pure options. Well, but what's the default mode? By default, Scala runs in the imperative style in terms of execution of expressions. Unlike Scala, by writing lines 8 and 9, there's an implicit implication here. And what is that? That the first call to get input will be over before the second call to get input is over. Nobody in this room is surprised about that, right? But if you're a pure functional programmer, you'd be very surprised at that. Because you would say, why? Because those are just two calls. We could use referential transparency. Of course, if I run this code, it's going to ask for the first input first and the second input after that. But like I said, I'm going to simulate this just a little bit. So I'm going to say lazy, and I'm going to define this as lazy. So what does lazy really mean? Lazy in Scala means don't really do it until you no longer can avoid it. This is like some employees at work, right? They say, hey, how's it going? Really good. Are you done with this report? Oh, that report, yes, I'll have it by afternoon, right? So they just kind of delay it until they no longer can delay it. So notice what I'm going to do here. I'm going to say if math.random is, let's say, greater than 0.5, then I'm going to say input 2 times 1.0. So this is kind of silly. I'm just asking input 1 to be available randomly at some times. Let's go back here to the command prompt to run this and play with this. So let's go here to where my code is. I'm going to go to the Scala directory where I have the code sitting. So right here, I'm going to say, let's see what we have in this directory. Oh, wrong place. Let's go to the Scala directory. So there we go. So right there, I'm going to say in here, Scala sample.scala. So I'm running it. Well, in this case, is it rand? Let's try rand. So I'm running this. Object rand is not a member. Is it uppercase math? So in this particular case, all right, so where is random coming from? Anybody remembers? All right, so there you go. So math, it was an uppercase M that was needed. So I say random 5 and 6. Notice it's -1. Run it again, 5 and 6. Hey, this was called dumb luck. Notice it's different this time. It was -1 the first time, 1 the second time. Of course, I said 0.5, so it's 50-50. So it behaved like the way it's supposed to, right? I wish life was this kind of predictable. But anyways, so notice the value was -1 the first time and 1 the second time. Why? And the reason really is because I said at random time, access input 2, if the value was greater than 0.5, we called input 2, so it ran this actually first. On the other hand, if you really want to see this a little bit more, let's go ahead and say input 1 and let's say input 2, just for the fun of it, right? So in this say message and let's say string, just to get a feel for it. So please enter a number 4 and then I will say message. So we can actually see the content coming through. So if I were to run this code now, you can see input number 1 and then I say 6 over here. And if I run this again this time, well, actually, let's try this one more time. The randomness is not random anymore, as you can see. So if I run this, you can see that it should ask for 2. There you go. So you can see it's asking for 2 this time and not 1. And that's because the idea really is that it decided to use input 2 in random times. Otherwise, it's using input 1 before using input 2. So in other words, there is no guarantee of the execution sequence of these two methods. Like I said, I'm trying to simulate the experience, a feel for what it would look like in Scala, but I have to admit, I cannot do this in language like any language on the JVM, because on the languages on JVM, the sequence in which you write the code is the sequence in which it runs, unless of course you throw threads, then you got that kind of behavior, right? So we're simulating that here, whereas like I mentioned, a language like Haskell, that's the normal way of execution. And you got to get a little token saying, excuse me, I want to impose a sequence here. So what's a monad in that context? Well, the way I look at a monad is a way for us to explicitly sequence execution of code in otherwise a world where referential transparency is the default behavior. So that is essentially what monads bring to the table, is a way for us to sequence. So if you look at language like Haskell, either you have to use something like a do, or there are other constructs you would start providing where you would start saying that this is it has to be done sequentially, and the way you do that is by marking methods with a little IO to indicate that this is going to involve an impure operation. So that is often is called a monadic sequence in terms of how the monads will work together. So what do we expect from a sequence of operations in general? Like I said, I'm going to struggle with this because we're going to talk about something that is not quite evident in languages that we are programming. So we have to kind of keep that in mind when we look at some examples. And that is one of the reasons why we don't have to get as much excited about monads in languages we program in, because we live in this world of impurity most of the time. And sequencing is something that happens all the time. It's not something we have to explicitly ask for. So it is something that we don't really have a very important need for in what we do mostly in these languages. But it's a good idea to learn about this, mainly because I'm sure there'll always be people who want to scare you with the word monad, but it's what is it? We know what it is by understanding the purpose and the problem it's trying to solve. Any questions before we move on with a few more details? Questions, comments, anything? All right then. Well, so what does it mean to really be having a monadic sequence? Now, this is where it begins to bend our mind a little bit. And I want you to think about this a little bit with yet another example here. If I say add op1 and op2 equals op1 plus op2, notice that this method takes two parameters, op1 and op2. But if you look at the output, though, there is a bit of a surprise here. Just look at that for a second, and that can be very confusing at the least. And you say, what in the world is that? Well, remember, functional programming really was introduced way back in time, even before we had really computers to evaluate and execute functions. This came from lambda calculus in category theory. And in lambda calculus, what we have is a function, and functions are considered to be pure, like we said, but functions also work with a single input. So functions don't take multiple input. Now you may say, why in the world wouldn't functions take multiple input? And the reason is, these people were interested in proving correctness of algorithms. Now, nobody in this room cares about correctness, right? I mean, we live by producing bugs, right? And so why would we want to make things correct? That's kind of boring after that. But they wanted to prove correctness. And they realized if a function were to take multiple input, you know, in math, you remember this, right? You don't solve a variable with too many, you don't solve an equation with too many variables. You assign constant to most of the variables, and then you solve one variable at a time. That's just not only easy, but it's easy to prove correctness as well. Well, so they said functions can only take one input. Now, think about this. What if we live in a world where functions will take only one input ever? Now, that becomes a little bit of a problem, right? So, for example, if I were to write a function called echo, where I send the input, and it simply gives me that input back as an output. So I can call echo right here. For example, I could say echo and send a 5, and it simply echoes back 5. Well, this is very easy. So if I say echo, for example, A equals A, and what does it say? Given an input T, return an input T, right? T in this case is a type parameter, but given an input T, return a type of input T. In this case, it's the same output as the input. Well, that is very simple. So what does this arrow say? The arrow says function is a transformation. Think about it this way, right? A function is a transformation of an input to an output, right? That's all a function is. And with the purity in mind, a function is really a transformation function. Given an input, you get an output. So you could give somebody, let's say, for example, you can give a value and you can get an absolute value for that value. I send -3, I get a 3. I send a 3, I get a 3. That's an absolute function. One input, one output. But on the other hand, if you look at the function add for a minute, add takes op1 and op2 and returns op1 plus op2. Well, given this particular scenario, how do we deal with this? Because this seems to be taking two input and not one input. Well, you can transform add into a function that actually takes one input. And the way that you do this is, if you go back and revisit this for a second, now look at this function. What this function says is, I am going to give you one input A. Okay, only look at the first arrow for a minute. So let's transform this a little bit and see what this actually means over here. So in this context, if you look at this, look at it as that for a second. Now, what does that really mean? It says, given an input, I'm going to give you an output. Well, guess what the output is? The output is a function that you're going to get. So this function is no longer taking an input and giving you a result. It's taking an input and giving you a function. What can that function do? That function in turn can take one input and return an output. I know if this may hurt a little bit, right? It did for me. But once you kind of sink that in, it begins to make sense slowly. And so in other words, let's try to write this in the Java syntax for a minute so we can kind of get a feel for it. So public, let's say int add, and actually let's write this in Java 8 syntax. How about that? That'll be a little bit of fun to get a feel for it, right? So let's say we have this function called add. So public int static, let's say int add, and this takes int op1 and int op2. And what does this do? This says I'm going to return op1 plus op2. So if you were to call add over here, so I'm going to say add with, let's say, 4 and 5, it better return a value of 9. Great. But we're going to do this a little differently. What we're going to do is we're going to say, let's go back and say import, let's say java.util.function.function. Let's say I'm going to write a public static int add int op1, and let's change this a little bit. Rather than returning an int, it's going to return a function which takes an integer and returns an integer. So now I say return, given a op2, return op1 plus op2. So if you look at this for a second, this add is returning a function that already knows what op1 is, and it's going to add op2, which is being given as a value just now. So the way I'm going to use this is output over here, and I'm going to say output. And what am I going to output at this point? I'm going to say this is going to be, let's call it as add f. And so add f says I'm going to take a value of 4, and that is going to give me back a function. So notice that's a lambda we got, dot apply, and I'm going to send a 5 to it, which will give us the result, right? So in a sense, this is the normal behavior in a functional programming language, is that functions always take one input, and if you are writing functions that take 2 input, that's actually a function that takes 1 input and returns a function, where that function will take another input and return your output eventually. And this, of course, we call it as lexical scoping, where it has cached the input variable over here. But what's the benefit of that? The benefit is we can do something like this. We can say function integer, comma integer, and then I'm going to say add, let's say add 4 equals, and I can say add f4, and now I can call this multiple times. Add 4.apply, and this could be 5, for example, and I can add a 5 with 4, but I can also go back here and say add, let's say 7 to this value, and 7 plus 4 is 11, and we can see that we are able to reuse that add function, which has cached the value. Well, this in Scala terms, we call it partially applied functions. Partially applied functions are functions where you can take and apply partial values. Let's get a feel for it right here in Scala. So I'm bringing the Scala REPL here. So I'm going to say define add op1 comma, let's say integer comma op2 integer, and this is going to return, let's say op1 plus op2. So that's the result I'm going to return from here. Now we can call this, obviously, we can say call 1 and 2, we can run this directly, but rather than doing this, I'm going to say over here, val add 4 equals add, and I'm going to say 4 comma, and I'm going to not provide the value for the second variable. So now I can say add 4 and send a 5, and add 4 and send 11, and I just did what I did in Java a minute ago with a lot more concise syntax, but that's called partially applied functions. So add 4 is actually a partially applied function. It's a function that returns to us another function we can exercise later with one value cached in already. So the point really about all of this is we are really dealing with a sequence of operations we're going to perform. So let's think about how we would perform some of these operations. So perform one action, discard the result of that, and then perform a second action. Now remember, we're talking about sequencing at this point, so we could start writing this kind of a sequence of operation. So for example, print something and then discard what you did and just print another result. This is like 2 print statements. Now, why can't I just not put 2 print statements just like that? Because the sequence matters. So how do you sequence them? Well, you represent that with this monadic sequence that you perform one operation, discard the result, and you perform another operation. That is just a representation of your intent to perform the sequence of operations. Or you can say, perform one action, pass the result on to the next action. So in this case, you could say, read an input and use that input to perform another operation, say, print that out. Well, you could represent it this way. You call a function, it sends a result, a value, to the next function. So that's why there's a parameter coming in to the next function, and that will use that result, and then you move on to return nothing from it. So you can start providing some sequence of these operations. Let's try to experiment with one of those here in Scala to see how that might feel. So here we have this get input, and what if I really want to enforce this sequence? Now again, I want to emphasize, we don't have to do anything to enforce the sequence because that's a default mode in Scala, right? But pretend that somehow Scala became referentially transparent tomorrow, and you want to really implement the sequence. How would you actually do that? Well, this is actually used in Scala. You probably have seen commands like and then, which provides a nice composition of functions, which can be very powerful. But the composition really happens for an entirely different reason in Scala than providing referential transparency, really. But like I said, these concepts are really alien to a lot of us because we don't share the same concerns as purely functional languages impose on us. So it's something that we don't quite, it's like going to a area where certain problems don't exist or certain features don't exist, and you're trying to explain it, right? So that's kind of where it's very hard to connect to it. But nevertheless, let's kind of give it a try. How would we go about doing something like this? Well, I simulated here with the lazy evaluation, as you can see, but instead of that, let's try something else a little differently. I want to sequence through an IO operation. I'll come back to that in a minute and show you how we could probably do that. So what's a monad? Well, it's really from the category theory. It is a way for us to explicitly enforce a sequence of operations. Like I said, if you're in Haskell, the default is the sequencing. And so if I were to run these two, you can see he's going to really run through and provide the value. Let's make this echo again. And he doesn't have any problems. But if you don't impose the sequencing, he gets very mad at you. So that is an example of a monadic sequence to say, I want to go through this sequence of operations. So a monad has a type constructor, if you want to really look at the type information itself, and it provides a way to chain these functions to perform certain operations. So in this case, let's see what this means. It says, given a particular input, a function, I'm going to take the result of that function and pass the result of the function to the following function. So that is a monadic sequence where we have one side effect producing function, and then we take the result of the side effect producing function and feed it as an input to the following function. Now the sequence is very important because without the sequencing, the two calls are referentially transparent, and we don't have a control over the order in which they can run, but because these two are having side effect, we want to explicitly force the sequence behind these two. So it's a way for us to connect them or chain them. Some languages provide an operation called the bind operation, where we bind the result of one call as an input of the next call. So that's another way to enforce this ordering. And of course, there are some variations of it where we can ignore the result as well after binding. There's also a function of injection we could do, where we could inject a new value into the sequence when we start going through the monadic sequence from the beginning. And we can also have monads where we simply tell them to return the given input. These usually are called identity. They simply return back the values that they get. So a monad is essentially a type in that context, and you could say that the identity type is where it returns a value. So how does this feel in terms of the functions we are used to? How would this work like? If you look at the and then function in Scala for a minute, let's look at an example of this. Suppose you write a function in Scala. So if a function takes one parameter, you can say function and then function 2, you could write like this. And this simply says execute function 1 and take the result of function 1 and pass it to the function 2, and you can carry through these operations. Shall we give it a try? So I'm going to say val f1 equals, let's do an increment operation here. So given an input x, let's say, I'm going to say equals x plus 1. So I could call this with, let's say, a value of 5, and you can see in this case the value is going to be the value incremented by 5. So let's by 1, and you can see the value is 6. On the other hand, if I were to say, let's say another function f2, and I'm going to pass the value, let's say 6 to it. Well, let's say this is going to be doubling the value. So I could say given an x integer, and we could say this is going to be a value of x times 2. And if I run this, of course, you get the value of 12. Let's change this a little bit. We'll call it inc, and we will call it as double it. So now I'm going to say inc and double it. So you can see in this case, this operation is incrementing and doubling it. But we can also do something like this. We could say inc and double it. So for example, we can combine it, double it. And what is this going to be? We could say inc and then double it. So for example, if I say inc and double it, let's print this out. So I'm saying inc and double it and send a value of 5. So what is that going to do? Well, it increments the value 5 and then it doubles it. But the essential idea here is, notice we took two different functions and applied a monadic sequence on those two, and that is an and then function. So even though we are not battling the problem of referential transparency here, the concept is not totally lost on us. We can start putting these compositions very nicely, and this is something you're going to do very extensively in Java as well. So for example, let me show you a quick example in Java how this would feel like. So if you're programming in Java 8, that is, you could do something along these lines. You could say, this is going to be in Java, I'm going to say function, let's say in this case integer, comma integer, and I'm going to say increment equals, so given x, I want to simply say x plus 1. So now I can say inc.apply, and this is going to be, let's say, a value of 5 to it. So this is going to be an increment operation. But to understand this, let's say static void print, let's say, value, and let's go ahead and pass a function over here of integer comma integer, and we will call it as fun, because it really is. And then we will also send, let's say, an integer, let's say input. So given this particular input, let's output fun.apply and let's say input. So if you look at this particular example, we could pass the increment over here to say print value and 5 comma inc as a parameter, and we can see that it incremented the value. Likewise, in Java, we could say, for example, oh, let's call this as double it. And in this case, I'm going to take a value and simply double it. So we could call this, for instance, and say print value 5 comma double it, and you can see the value is being doubled. But likewise, we can also say print values, and in this particular case, we could say 5 comma inc, and we could say, so we could say, and then, and what do I want to do here? Double it. So we could start combining functions together in Java as well, and you can start seeing the monadic sequence coming into play again. So we can put together functions and combine functions and perform these kinds of operations, and that's something we could effectively do. So how does this actually feel when we write it without this kind of a concept? Well, the idea is this. If you say F bind G, so replace the word bind with and then, if you will. So F and then G, what does that mean? Well, first of all, call F with the value V, whatever is the parameter given to you, take the result of that and pass it to G. So in other words, if you look at the code over here, this is essentially saying something like int temp equals, and then you could say increment some value that you are interested, and then you could say result equals, and then you could say double it, and then you could pass the value of temp to it, right? So essentially, of course, in the case of Java, you would call apply in these cases, but the idea behind this is still the same, is that, so if you want to really try this, writing it a little differently, you could output the result over here, but you can rewrite this as, rather than result, you could say double it dot apply, and then inc.apply, and then the value 5, which is what you're trying to run through here. So that looks a little cumbersome, but that's essentially the idea. You invoke the first function first, take the result of the function, pass it to the other function, that becomes the sequence, but that's a lot more expressive by writing it this way than the ugly nesting that we get into, right? So that's basically the monadic sequence and the flow that we get. Well, bind is associative. What does that mean, it's associative? Well, it means X bind Y bind Z is the same as X bind, and then combining the result of that with the Y bind Z. So you could actually go either way in combining these things. Well, now we saw one kind of a monadic operation, which is a sequence of operation. But there are other kinds of monads we can use as well. Now, why are these called as monads? Well, the reason again is there is a certain amount of emphasis we want to place on either an ordering or a behavior or a formulation or a composition, whatever that could be. Let's look at one example here. Let's say we are back here in Scala, and I want to define a collection of values. So let's say val map equals, and let's say in this case A, and that's going to be a value of 1, and B is going to be, let's say, a value of 2. So in this case, I want to simply print the value of map that I want to see. But I want to get a certain value from the map. So I call get with the value of A. Notice very carefully what the result is. The result is not 1. The result is sum 1. Now, why is it sum? Likewise, if I say print over here, and the print in this case map dot, let's say get, but I don't have a Z, but notice it's a none. And the reason for this is returning an option as a result. And an option contains two types of values. It could be a sum value when there is actually a value given to you, or it could be essentially a none because the value doesn't exist. So usually this is called as a maybe monad, and may or may not be exist, the value may or may not exist. You can see this in Java as well quite effectively, for example. So if I'm in Java, and let's say I'm interested in taking a list of integer values, and I'm going to say in this case, given this list of integer, let's call it as numbers equals, and arrays.asList, let's say these values, and I want to get the first even number greater than, let's say, 5. And I want the first even number greater than 5 from the sequence of some values that I have in this particular case, right? So how would I get the first number that's greater than 5, even number greater than 5? So I would simply say in this case, along the lines of numbers dot, so we go to a stream in Java 8, we can do a filter, and the filter is going to be given a number, I want to make sure it's greater than 5, another filter operation, given a number, I want to make sure it is even number, and then I'm going to say find the first one that's available to us. Once again, notice the nice compositional aspect here where these functions line up. But what is the result of this particular call? Notice it's optional again, and the reason is such a value may or may not actually exist. So in this case, the result does exist. But what if there is no value greater than 5 at all, even though there are even values? Now notice it gave us an optional empty because such a value doesn't exist in the collection. So this is very preemptive in telling us, I cannot give you a result. It may or may not exist, and you have to deal with it. And it may influence a change in the sequence in which you follow further, because if it's optional, empty, your results may be very different from if it is not empty. So you would have to decide on the course of action this function is going to return to you, so you may have to do that. A couple of more examples I'll give you is one thing called an I/O monad. Now, I/O monad is like the common thing in language like Haskell. When you're returning, when you're doing some operation, you would normally say this is going to be an integer, which is going to be an I/O. Meaning it's an impure operation. So think of I/O as not input-output. Think of I/O as really an impure operation, if you will, right? So you can do an impure operation along the way and force a sequence or a chain of operation on it. So how would you do that, let's say in a case of Scala? Let's take one example. So I'm going to say object, let's say I/O, and I'm going to define a special function. And this actually is a syntax from F#, and I'm kind of stealing that here in Scala because it looks really cool. And in F# you can nicely put sequence after sequence after sequence and nicely flows through. And so in this case, I'm going to take a function. So what is the function I'm going to provide here? Well, let's write this part first, then it's easier to see what I'm going to do. I'm going to write a function where this guy says, give me an input x, and I'm going to print the value of x that you gave me. So in other words, I'm enforcing a sequence of ordering in this example. Now, let's take a look at this. This def is for defining this function. That function is on I/O, which is already there. But what is the remaining of this function? That is a function itself. So I'm going to say this is a function, f. But what does this function do? It takes an input, let's say it's a string, and what does it return? I don't care what it returns. It could be a unit, it could be a t. In this case, it's a parametric type, meaning I don't really care what it is. You can infer that later. So what am I going to do here? Print line, let's say enter a number. So I could ask for a number to be entered. We'll just say print. And then I could simply say that the value input equals, let's say standard in dot read line, and then I could say function and send the input over. So in this case, what I've done is I have said this function is going to ask for an input, take that input, send it to this other function, and that is the sequence operation that I'm doing right here. Let's give that a try. So I'm going to say Scala and run the sample code here. And it says enter a number, let's say 5, and it printed a 5. So that's a way for us to enforce a sequence among calls when that sequence is important. Now you may say, why would you want to do something like this? Imagine you are writing functions which can be parallelized, but there are certain parts in the parallelized function that do have to be done sequentially. You could go along some of these lines where you can say, here is a branch of code that can be done in parallel, but within this branch, I want a sequential execution for these, and you can start enforcing some of those sequences as well, and that is one way. But I'll show you one other example that could be a little fancy to implement. I want to call this the logger monad. So I want to quietly do logging if I've started logging at some point. So to do this, what I'm going to do is create a class called a logger, let's say. So what does this logger do? The logger says, I will do logging, and I'm going to use a poor man's logging here, writing to the console, but you could do any fancy logging with this as you want to. So define, and I'm going to use the same symbol I used, and what does this do? It's going to take an input, do a logging, and pass on that value to the next function in the line. So I'm going to do something like this. I'm going to say logger, let's say 2, and I'm going to pipe that to, let's say in this case, given a value x, I want to say x plus 1, and I want to pipe that to another function, let's say x, and that's going to say x times, let's say 2.2, and then I want to pipe that to, let's say, the last value, and this is going to say x, let's say, minus 1. So I want to log each of these results in between. Well, how would I achieve that? Well, let's again go back and understand the format of this. That's a function. What does this do? Well, it's a function too, but that function is a parameter to the def function, right? So f, and what is the input type of this function? Well, in this case, x is an integer. Great. In this case, x is an integer, still good. In this case, x is not an integer. It is actually a double value. So in other words, I don't know what the type is going to be. Well, the type is going to be t as coming as an input, and the type output could be something else. Let's say it's going to be t2. So I could have a function that takes a t1 and outputs a t2, and so these could be parametric type t1 and t2, for example, right? So that function is a transformation of t1 input to a t2 output. But within this, what I'm going to do is print out, let's say, whatever the value that we have on our hand coming in, and what is that value going to be? Well, that is the current state of this object, whatever the object state is. So I'm going to make this a value object. So this is t, and this is going to be val, let's call it as value, which is of type t. So print the value and then call the function and pass the value to it. So in other words, what I've said expressed over here is I've said that I'm providing this very quiet, silent logging along the way, but the way I'm going to do that is I'm going to capture the current value into a variable, and then I'm going to log that value, in this case, poor man's logging printing, and then pass the value to the subsequent function that's in here. So that is all I have done in this particular case. Let's fix the error. Line number 4 is not happy with it. So line number 4, of course, this should be the value, whatever type it is, right? Let's say t here for a second, whatever type that's coming in that it's going to work with. So with underlying type t, type mismatch found logger, this value t, let's see why that's complaining at this point. So this is going to be the value given here. So that should know the value that's up here with this. So let's actually see where the error is coming from. What line number? Line number 4. So he's having trouble with the value to f. Oh, I know the reason for that. Because we are calling this function f, and the result of the function f is going to be the return value, which is here. Well, that's going to move on to the next logger up here, down the chain over here, isn't it? So once he gives the result over here, what should we do? We should create a new logger, right? New logger, because the result of that call is another logger, and then I'm going to pass that over as a new logger in the result. Let's see. So anyone sees the problem here? So a type mismatch, found logger, this value, type, underlying type is t, require t. Hey, that's very, very useful. Type is t and require t. So I got to figure out why that's not happy with this particular sequencing here. But the idea is that I'm passing the type t to function.
You have 2 times the t, so the def itself should maybe
The def itself should be, oh, I don't need to put a t here, you're saying, because it's already a type t that's coming in. All right, so there you go. Yeah, absolutely, thanks. So just to make this work a little bit, let's say object, awesome debugging there. So logger, and I'm going to simply say define apply, and this apply, let's go ahead and say this is going to be a type of t that it's going to take. And what does this do? Oh, a value, let's say, is coming in of type t. I'm going to return new logger with the value that's given to us, right? So I can use an apply on it, so you can see the logging happen throughout. So 2, 3, and 6, but wait a minute, the last one, it never did it. So if you really want to capture the last one, you could call a ignore. Again, this is something from F#, which I really like. You can sequence through, and in the end, you can just say ignore in F#, so you can do a similar thing. So my ignore, what does it do? Define ignore. Ignore is a function that simply swallows what you give. So value of type t, and this is a just function that just ignores what it takes. So you can see the result 5 being displayed in the very end. You can do that. Or you can also define an implicit, and if you define an implicit, then you can remove this object logger, and then you can just convert it. But this is probably a little bit better than the implicit itself. So that is an example where you can start defining some kind of sequence of logging to do. So the idea is not just logging itself, but you are masquerading this with some operations and sequencing, and this can be pretty powerful if you want to implement a library where you are doing some kind of an IOP injection where some operation can happen in between depending on what you start with. And so for various purposes, you can start with the logger, or if you can configure it so that there's no logging happening, and then you can switch back and forth. So that can be very powerful set of operations to provide. But if you really look at this code alone, in fact, as I was saying, what about this? So if you were to just say 2 for a minute, right? So let's get rid of this for a second, and I'm going to say implicit, so implicit, and in this case, I'm going to define convert to logger, and let's say to logger. And then this would, of course, be something along the lines of a value coming in of type T, so whatever the type T is, then I can say equals new logger of the value. It's going to give a warning because I'm using implicit. Ignore the warning for now. You can configure the import to remove the warning. But the point really is focus on this here. So depending on what you are importing, a logging can happen and not happen. So this can be a very powerful set of tools to implement. And you can turn on and turn off features by just adding an import and removing an import. And then you can do fancy things with it. Of course, you got to be careful doing some of these too. And the last thing I will mention here is about a list monad real quick. This can be very powerful to do certain operations of filtering, for example. So if I have a list of values, let's say a list equals, let's say values 1, 2, 3, 4, 5, and 6, and I have these kinds of values on my hand, and I want to go ahead and do a double of even numbers, and you can see the monadic sequence through these again. So you can say print line, for example, list of filter, and given an element, I want to say element mod 2 is equal to 0, and then I want to do a map operation. Given an element, I want to do element times 2. So this gives us a double of the values that are even numbers in this collection, and that can be very powerful set of combinations to apply. So this again is a very important sequence. You cannot obviously do map before you're done with the filter, but this is a list operation, and you're just following through a monadic operation on the list, as they call it. Again, when you are using these things, you don't have to sit there and bite your nails and say, oh gosh, I'm using a monad, I'm special. Well, this is just a normal operation. Most of the time, you don't have to really think about it and talk about it. Similarly, you could use a flat map if you're interested to do the same operation here to achieve that instead of putting a filter and a map. So to summarize what we talked about, the idea is monads are something that we often don't have to think about, don't have to really use when we program on the JVM. And the reason is because we don't share the same set of problems that we share as purely functional programming languages are. But knowing what monads are is something that's helpful because A, it at least helps us to cope with those other guys who keep talking about monads to us all the time, and we know what the real intention is and where it applies in pure functional programming languages. When it comes to monadic operations in Scala or other languages, these are pretty much built into it, and most of the time we don't have to think explicitly about monadic operations, and there are maybe certain times when you are really trying to sequence a sort of operations or achieve a certain behavior, and yeah, it might be helpful to really think about a monadic operation, but for 99% of the time, we don't have to focus on those things. I would rather get the practices as a normal things we do under our belt, rather than thinking about a monadic sequence or monadic operation and then try to spend the time on, how does that look rather than solving real problems. But I hope that's useful to know what monadic operations are. Any questions, comments before we wrap this up? Please.
Reactive extensions, are those a form of monads too?
So the question is, are reactive extensions forms of monads too? Well, you could argue that they are, but to me, the main power in reactive extension is not whether they are monads or not, and the fact that they actually are resilient, or responsive, or efficient. That's really what I want to focus on when it comes to reactive. The fact that it may be a monadic sequence is really not that important in my opinion. Any other questions? Well, that's all I have. Thank you.